Hello, for data communications and network one class today, Ajahn Usuna will talk about linear block codes. Linear block codes is a type of error correcting code that we using a lot. Okay, so we mainly focus on the code that can correct errors. Okay, in this topic, we define this as an NK code with two parameters and NK. N is the number of bits in the code word, okay, and K is the number of data bit. So the number of priority check bit is N minus K. Okay, so we have N minus K priority check bits. So how to compute the priority check bits? The data is given from the user, right? But the priority check is the redundancy that we add into the data, okay, to make a code word. So we compute this one with modulo 2 addition, okay. For example, we have a 7-4 code, okay, with n equal to 7 bit and k equal to 4 bit. So the data bit is 0011, and I color code it, okay, like this, so that you can see how to compute the priority bits. The first priority bit, okay, this one, the red compute from the blue, the pink and the violet, okay. So basically it's this one, and this one. So you add together with modulo 2 addition and you get 1, right? So this is the first priority check bit. Modulo 2 addition is like this, mod 2 addition, okay. It is the same as XOR gate or exclusive OR gate, okay. And the operation look like this. If it is the same value, okay, two of them are the same value, get 0. So 1 plus 1 is 0. If it's different, okay, they're different, then you get 1. So this is the operation table of the modulo 2 addition or the XOR gate, okay, in the digital logic. Okay, the second bit here, the dark blue here, is computed from the light blue, the pink, and the green. So light blue, pink, and green, okay. So you add modulo 2 addition 001, so you get 1, okay. So this is the second bit. Now the third bit, comes from the light blue, the violet, and the green. Light blue, violet, and green, okay. So you get 011, so you get 0, add to 0. So this is the last bit of the priority check, okay. So what is the code word? Code word is data here, and this is parity that you compute, okay, check bit. So data and check like this. I note here that most significant bit is on the left. Most significant bit means that the most important digit, right, or the most important bit, okay, which is this one, is MSB, okay. Why do I have to note this? Because when you send, okay, into the channel, okay, you send most significant bit first. This is most significant bit. So basically you send 0011 110. This is the most significant bit. So this is the code word that you send, and then you receive the this is the receive sequence. Okay, so you send the code word and you get the receive sequence. Now let's talk about cyclic code. Cyclic code is a very important code. Subset, it is a subset of the linear block code, okay. It is a very widely used code in practice, okay. If you have heard of the CRC, cyclic redundancy check, it's the same. Sometimes you heard this name, okay. So this is the cyclic code. It is the same as the cyclic code, okay, and you heard it in when you talk about the protocol, okay. it is easy to implement, okay. The encoder and decoder is easy to implement with the chip register circuit, okay, and we'll talk about this later. Okay, now how do we compute the parity check bits? Okay, instead of counting the number of ones and zeros as in the odd parity and even parity in the last slide, we have to compute in a more a little bit more complicated way. Okay, so I didn't show the proof of the math here. I have a sheet, so if if you want to read about the proof, then you can ask me. And also I'm teaching another class called Applied Coding next semester, so you can also take that class to learn more about channel coding, everything about channel coding, and also other codes like encryption. Okay, anyway, we select the parity checks, okay, so that all code words are divisible by a generator sequence, which I will denote as the vector G, or generator polynomial, or GX, okay, in terms of polynomial. Okay, so when you have, for example, you have 7-fold code, and then you have so you have 4 bits for data, right? So data have 4 bits. So you have the value 0, 0, 0, 0, 0, 1 until 1, 1, 1, 1. So you have 16 case or 16 patterns here, which is equal to 2 to the 4, which is 2 to the k, okay. K is the number of data bit, okay. Then you send the data, okay, to the encoder, and then you get code word, right? Now the code word has 7 bits. 7 bits. But when you transmit, because you have only 16 patterns of data sequence that you can transmit, right? So you also have 16 values of code words. So you have it's going to be like 1-to-1 mapping. Okay, so you have like also 16 pattern or 16 cases of code word, okay. However, when you send code word, so you have code word, okay, you send to the channel, then you get receive sequence, okay. So this is the receive sequence can have some error, okay, and this is 7 bit. So they are equal to 2 to the 7 pattern of possible receive sequence, right? Zero, zero, zero until 1, 1. Okay, so 2 to the 7, which is 2 to the 7 equal to 128 patterns. Okay, so in this case there will be only only 16 code word, right? And another another 100 sequence are not a code word. Okay, so what do the receiver do? Receiver want to check for errors, okay. So receiver will try to separate between the 16 code word, okay, and other sequence that are not code words, right? If it is if what it is received is a code word, then it will say that there is no error, okay, assume no error. But if it know that it is not a code word, that it is true 100% that there are some errors in the receive sequence. Okay, so what do they do? The receiver will divide the receive sequence with the generator sequence. So you do like this. It will find the remainder of R divided by G. Okay, and check if it is a zero vector or not, if it's zero or not. So if it is zero, if equal to zero, receiver assume no error. Okay, assume no error. If not equal to zero, so there's some remainder, then receiver know 100% there are some errors in receive sequence. Okay. Now, why do I use assume here? Because if you send like a code word, for example, you send code word or zero code word. Okay, but you receive something. Let's say you receive look like this. For example, you receive like this. Suppose this. Okay. So there's error here, right? The 3 bits here are in error, but it look like another code word V. Okay, then you cannot suppose, okay, accidentally it look like another code word V. Then the decoder cannot separate, cannot tell that there's something wrong. Okay, decoder can do only separate the possible code words, okay, from the not code words. Okay, if it is one of the possible code words, it will say that there is no error. This is the best that it can do. Okay, so there will always be some undetected errors. Okay, but the undetected errors, if you design well, the undetected error can be very low. Okay, the probability of undetected error can be like 10 to the minus 6, 10 to the minus 7, something like that. Okay, but it cannot be 0. So when you decode something, okay, decoder cannot be 100% correct. Okay, it can be 99.99999 correct. Okay, which means it make correct decision. Okay, but it cannot be 100% that it make correct decision. Okay, because it's always cases that error patterns make one code word look like another code word, then decoder cannot detect it. Okay. Now, how do we encode cyclic code? Okay, we must know its structure or the parity, or the generator polynomials gx or the generator sequence g. Okay, this must be given to you. How to find this is in another class that I'm teaching, applied coding class. Okay, next semester. Okay, there are 3 methods. Okay, to encode. Okay, all of these 3 methods must give the same answers. Okay, so if you do the first method and you do the third method and they are not the same, there must be something wrong. Okay, they must give the same answer. So we have data bit coming in to the encoder and we get the code word, right? The model to arithmetic and the polynomial, they are very close together, very similar method. Okay, but the model to arithmetic deal with the binary sequence and the polynomial deal with polynomials. Okay, the coefficient of the polynomials is basically the sequence in the modulo to arithmetic. I will show you in examples. Okay, so you know more how to do it. Okay, and the third method is the chip register circuit or the digital logic. Now, look at the first method, the encode by modulo to arithmetic. Suppose I give you the message u. This is the vector u. Okay, if it's bold italic. Okay, variables with bold italic means that this is a vector, okay, so that I don't have to put the hat in the typing, okay. So anyway, so data or message, okay, we can call message or data, okay. So U is 1001, okay, this is a 7-fold code. So k is equal to 4 bit, right? This is the most significant bit, okay. We talked about the generator sequence. This is generator sequence 1011. What is the corresponding GX generator polynomial? Generator polynomial use the coefficient from the generator sequence. So this is the most significant bit, right? So x to the cube plus x plus 1, okay, plus x plus 1. So this is GX. The degree, the highest degree of GX equal to n of minus k always, okay. So the coefficient, okay, always, the generator sequence always have the length of n minus k plus 1, okay, because you have the coefficient of x to the 0, right? So it's always n minus k plus 1. So this is the generator sequence. And we want to find the parity check sequence and the code word, basically. The code word we call it vector v. Parity check sequence called vector b. Okay. So first you have u equal to 1110, right? Then you shift it to the left, okay, by the number of check bits, okay. So you multiply by 2 to the n minus k. So you multiply 2 to n minus k, which is equal to 3. So you get 1110, and then you add, you have like shift it to the left, so you have like 3 more zeros here. And this one you will, when you compute the code word, you will have the data here, and you get, this is the b, okay, here, and it become code word. So this one you have the data, which is most significant bit here, and this is the parity check, okay, with, again, this is the most significant bit of parity check, okay, and you add them together and you get the code word. Then you divide the 2 to the n minus k with u, multiplied by u here, okay, with the g. So this is g, this is 2 to the, so you divide, let me show it again, okay, although it's over there, so that you can see how we compute this. Basically this is 2 to the, okay, and divided by g. So g is 1011, right? We can write it as u and divided by g, like this also, okay. When you divide, okay, so the first non-zero, okay, so you put it here like this, and then you get 0 1 0 1, okay. Usually you will minus, right? You will, like, the upper line minus the lower line, but in this case it's modulo 2 arithmetic, as I showed you before. Modulo 2 is like this, so 1 minus 1 equal to 0, and 1 plus 1 is also equal to 0. So in modulo 2 arithmetic you can always just add them, okay, using this operation table, okay. So you have 0 1 0 1 like this, and the 0 will not be counted, right? So you have 4 bits here, so you have to add another 0 here so that you can continue division, okay. So the 0 will not count, so we start with the 1 here, and then you have another 2 0 here. This is 3 bit, which is less than the 4 bit here, so you cannot divide anymore, right? So this is the b, this is the parity check sequence, and you add the b at the end, okay, after the shifted u, right? So then you get get u here and B, okay, next to each other, right? And then you get the code word. Okay. So this is the end of this slide. For the next slide, we will continue with the polynomial division. Okay.